name is Andre Williams. I will be presenting on Autoencoder-K-means algorithm for anomaly detection. Before I begin, I'd like to send a thank you to my colleagues, Dr. Ahmad and Hamid Akbarian, for allowing me to present on our research. I'd also like to send another big thank you to SmartNets and James Madison University for allowing us to attend this conference. So first, we'll do some house cleaning for the agenda. We're going to discuss the problem statement. We're going to talk about an introduction, a background. Then I'll discuss the algorithm. Then we get into the results and how it performed compared to the related works. We'll discuss future works. And finally, we'll discuss the summary. So now, currently in space operations, most anomaly detection systems are rule-based, which can work for single-dimensional data, such as battery voltage. If it drops below a certain level, it's an anomaly. But as we delve deeper and deeper into deep space, we're going to need more intelligent methods of detecting anomalies in more complex, multi-dimensional data spaces. So with this being said, there is a need for artificial intelligence and machine learning to be applied in this realm of anomaly detection in deep space. Anomaly detection is the process of identifying unusual patterns or data points that deviate from expected behavior. Now, every anomaly detection algorithm has four main stages. One, we're going to fit our model on normal data so it can understand what is expected behavior. The second step is to determine the error on the test data set or the data set with an anomaly in it. Then with that, we're going to compute our anomaly score. And from there, we're going to perform thresholding. There's three common methods of thresholding. That's static, a global threshold. So if it rises above this level, it's an anomaly. There's a mean plus n standard deviation. So if it's so many standard deviations away from a mean, it's classified as an anomaly. And there's a peak over threshold. So where the threshold continually moves up whenever we have a peak in data set. So anything that goes above that peak is an anomaly. So now some of the more advanced evaluation metrics, we have precision. So precision is out of all the predicted anomalies, how many were correct. We have the recall, that's out of all the actual anomalies, how many did the model correctly predict. Then we have an F1 score, which is the balance between the two. Let's highlight the three different types of anomalies. We have point anomalies. That's where a single data point is so different than the rest that it actually stands out. We have a contextual anomaly. That's a type of anomaly that depends on the context of a situation. It's mostly temporal. Then we have collective anomalies. That's when a group of data points taken together are unusual. But if you look at one data point alone in this group, it might not seem strange on its own. Overview of the characteristics of our SMAP dataset provided to us by NASA. It has every channel has 25 features. So when you think of a channel, think of one channel for radiation, one channel for battery, one channel for orbit. And each channel has 25 features. One feature, which is the actual telemetry value, which is a float, and the remaining 24 are binary features. They are the commands that were sent and received to each module on the spacecraft. So now we will get into the architecture of our AE-K-means model. So the central core of our model is the autoencoder, which is composed of two different components. An encoder, which compresses the original data set down to a richer feature space. It eliminates noise and useless features and gives us a rich latent space. Then we use a decoder to take that latent space and try to reconstruct the original signal. Going to get into the K-means implementation. So we have two data sets. We have a training data set, which has no errors, it's normal data. Then we have our testing data set, which has an error in it, either a point or a contextual. We feed our training data set to the autoencoder so it can train on that data to understand and learn what is normal behavior. Now we're going to leverage the latent space provided in the autoencoder. So we transform our training data set going down from 25 features to 8 features, rich latent space data. Then we transform our test data set going down from 25 features to 8 features. Now, with this rich latent space, we can use the training data set to define our clusters and our k-means. So we use the training latent representation to find the number of clusters and the direct orientation of those clusters. Then we're going to use the test data set to assign each row in the data set to one of the clusters that was defined with the training data set. Based on that, we can get a distance from our assigned cluster to the actual data point, and we can determine an anomaly score. Further clarification, this illustration is showing that the red X's are the cluster centers. So with normal data, we define where normal data normally clusters. And then you can see the colored dots or data points from our testing data set. And intuitively, this should tell you that the closer the data point is to what's defined as a normal cluster, the more normal that it is. So now we're going to discuss the second phase of our anomaly detection algorithm. Now we know that the autoencoder is trained on normal data, the training data set. So intuitively, it understands what is normal, and it might struggle to reconstruct an anomaly. So we're going to try to leverage that, and we're going to reconstruct the test data set, but we're going to do something different here and try to reconstruct it in slices. So think of it as a 100 time step window, but it's a sliding window or a rolling window where it rolls over the data set. Now, when it comes across this point anomaly that's shown here in this illustration, you can see that it's going to struggle to reconstruct the point anomaly, and we're going to have a higher MSE score. Here is our pseudocode, so you can see the method in which we produced our two anomaly scores. Keep in mind that we're going to have two anomaly scores. Thresholding. So we have two main anomaly scores. We have our k-means anomaly score and our reconstruction loss. We decided to go with a density-based approach because intuitively, most of the data is going to be normal, and normal data points should cluster around 0 reconstruction loss and 0 k-means anomaly score error. So we're going to have a high density of data there. Now, looking at the graph on the right, you can see how our algorithm models the data. Our data set has 8,000 samples, so 8,000 data points. So considering that most of the data should be normal, we chose a nearest neighbor of 6,000. Now, for each data point, all 8,000 samples, we're going to choose 6,000 nearest neighbors. And we're going to get the distance to each of those 6,000 nearest neighbors. So out of 8,000 samples, imagine 6,000 columns, one for each distance to its nearest neighbor. Now, with that matrix, 8,000 by 6,000, we're going to average it all and get our threshold. It's going to be one single float value. After that's done, we're going to iterate through each row of the 8,000 samples and get the average of all 6,000 neighbors. And if it's greater than the threshold, then it's going to be labeled an anomaly. If it's less, then it's going to be labeled normal. Now, our model is completely unsupervised, but we're going to use the labels here to kind of make things more clear. These are labels provided to us by NASA. The red points are anomalies, and the blue points are going to be actual normal data points. Now, ideally, most of our data, as we intuitively thought, the normal data clusters around 0 and 0, and our model shows great discrimination between normal and anomalies. Now, ideally, the green line is going to be our threshold. Anything inside of this green line, anything inside of this density bubble here is going to be classified as normal. Everything outside is going to be classified as an anomaly. So you can look at this and see a couple false positives, a couple false negatives, and our true positives as well. Here are the results shown in our paper as compared to the relative works. We use two different activation functions for our hidden layers in our autoencoder. We use a ReLU activation and a TAN-H activation, and they both yield fantastic results. Future work, we have two areas that we can possibly explore. One area is adding another anomaly score. So this way you'll have three different anomaly scores. And we're going to use a prediction-based anomaly score this time. So that will give us a clustering-based, a reconstruction-based, and a prediction-based, which theoretically should be even more powerful. Also, we're going to look at providing extra information by using feature engineering. So maybe we could take the average, maybe a rolling average of telemetry data, or we can get maybe like a rolling standard deviation, and this can help provide the model with even more information to determine what's an anomaly and what's normal. Well, finally, in summary, we feel that we built a very cool anomaly detection algorithm here. It's very powerful. By leveraging both clustering-based methods and a reconstruction-based method, it makes it very robust no matter what the type of anomaly is. A clustering-based approach is more efficient at finding points that deviate from the normal distribution of the data. Meanwhile, the reconstruction loss, by using this innovative sliding window approach, it is more efficient at picking up temporal contextual deviances from what's normal data. So by leveraging both of these, we created something that's very streamlined and it's optimized, and it can handle both types of anomalies alike. That's point and contextual. We have reached the end of our video presentation. Thank you once again to all parties for giving us the honor to present our research. Here you can see our email address. Feel free to reach out if you have any questions, concerns, or comments, and we will be more than happy to address your questions. Thank you.